Hi, today we will learn hysteresis and hysteresis law. These are the magnetic property of material visible in ferromagnetism. As we know that a ferromagnetic material has higher value of susceptibility and relative permeability. You can see in diagram. But actually, this is not the true taste of a ferromagnetic material. For ferromagnetism, the magnetic intensity and the magnetic field of the ferromagnetic material should not be proportional. So I have used some terms. Let me define in brief all these terms. You have a solenoid here, and you know that magnetic field of solenoid is mu naught Ni, where N is number of turns per unit length and I is current. Here N and I are external things. You can change the number of turn, you can change current. But permeability is the magnetic property of material. It is intrinsic property of material. So if you divide the two sides of equation by mu naught, so here you can see that permeability is cancelled from right hand side of the equation, and the equation is totally dependent now on extrinsic things, number of turn and current I, and this is termed as magnetic intensity. So B is equal to mu naught H. Here B is magnetic field and H is your magnetic intensity. This is one thing. Now you will appreciate that when any magnetic material is kept inside any solenoid, then due to field of solenoid, the material gets magnetized and has some magnetization. This magnetization M is due to external cause current, so magnetization must be proportional to magnetic intensity. And here constant of proportionality is called magnetic susceptibility, and this susceptibility chi should be higher for ferromagnetic materials. Now when it is magnetized and has magnetization, so it will now produce magnetic field. There will be magnetic field of the magnetic material itself, and let the magnetic field be Bm, which is caused due to magnetization M of the magnetic material. So Bm will be proportional to magnetization only, as it is caused due to magnetization of magnetic material. So from this equation 1 and 2, you come at the conclusion that magnetic field of the magnetic material is proportional to magnetic intensity for all the substances. But it is not true for ferromagnetic material, and this is the true taste of ferromagnetism. They are not proportional. For hysteresis, let us draw a graph between magnetic field of magnetic material and magnetic intensity. So magnetic intensity is related to electric current we are giving from outside. If current given in solenoid is 0, magnetic intensity will be 0, and magnetic field of the material kept inside is also 0. So you get a point over here. Now when you increase the current in solenoid, you will find that magnetic intensity is also increased, and magnetic field related to material kept inside the solenoid is also increased. You get this curve. Finally, you have a saturation point of magnetic field. Magnetic field cannot be increased any further. Here you have saturation point. Even though you are increasing the current and magnetic intensity. So this part of curve OA can be seen as alienation of all the domains and merger of domain. This part, your OA part of B versus H curve represents alienation and merger of the magnetic domains of the magnetic material. Now, here the current is highest and magnetic intensity also is highest. So you now decrease the current. Accordingly, the magnetic intensity will be decreased. And you will find that when intensity becomes 0, there is remained some magnetic field of the magnetic material. It does not come to 0. It is lagging behind. It is yet to come to 0. So you reach at a point B. This point B represents your remanence or retentivity. Here magnetic field is retained, some magnetic field is retained. So this point is termed as remanence or retentivity. External cause becomes 0 here at this point. Current becomes 0. Magnetic intensity also becomes 0. But magnetic field of the magnetic material kept inside is not 0. This is called remanence. So what is your remanence or retentivity? When the magnetic intensity is brought to 0, there is remain magnetic field in the magnetic material. This is called retentivity or remanence. Now, in this very graph, here your magnetic intensity is 0. Now you give current in the solenoid in opposite direction. So magnetic intensity will be increased in opposite direction. So you will find that the magnetic field in the magnetic material very increasingly becomes to 0 because all the domains which were alienated till yet is flipped This point C represents coercivity. This is your representing coercivity. Here C. So what is coercivity? C is a point actually on your magnetic intensity. You can see. So the value of magnetic intensity in reverse direction at which magnetic field becomes zero. This value is called coercivity. The value of magnetic intensity in opposite direction at which magnetic field becomes equal to zero. Of the material becomes zero. So this is your coercivity. Now if you further increase current in opposite direction, you again get a peak point. Here magnetic field cannot be increased any further in opposite direction. Even if you increase magnetic intensity in reverse direction by increasing current in opposite direction. So this point gives you saturation point of magnetic field in reverse direction. It will be represented by point D. So if you decrease the current in this direction, you get a curve DE. And if you increase the current now in opposite direction, you get a curve EA. So DE curve is obtained by decreasing current in the same direction. The current is decreased. Then current is increased in opposite direction for curve EA. And we get a curve which does not retrace its original path, OA. Now this curve is repeated again and again. This cycle is repeated again and again, and you will find that for one value of H, suppose here I have taken one value of H, that is your H1, you have three values of magnetic field. A value given here, a value given here for H1, a value given here, and a value given in downward direction. So you find that magnetization depends on history also. So you have three values of magnetic field for a single value of magnetic intensity. This is called hysteresis. There are different values of magnetic field for a given value of magnetic intensity. And you can find that this depends on history also. Magnetic field. Okay, let me write here. This is This is hysteresis, okay. So you find that magnetic field also depends on history. Now, you will also observe here that when magnetic intensity is brought to zero, magnetic field is yet to come to zero. It is lagging behind. This lagging behind is also termed as hysteresis. The lagging behind of the magnetic field is called field with respect to magnetic intensity. Is called hysteresis. The complete cycle, the complete curve is called hysteresis lobe. So we knew that the magnetization depends on history of the magnetic material. History of magnetization. And it also depends on magnetic state, thermal state, and mechanical state of the magnetic material. If you hit hard the magnetic material, or if magnetic material is in vigorous motion, to and fro motion, then its magnetization is affected. Now if temperature is different, temperature is very high, then also magnetization is affected as per Curie law. So Curie law suggests that susceptibility chi of the material is inversely proportional to T minus Tc, and this chi is equal to C upon T minus Tc. Here your C is Curie constant, and T is your Curie temperature. Tc is your Curie temperature for different substances, and this Curie law is for ferromagnetic materials. So ferromagnetic materials can be converted into paramagnetic materials if temperature is increased beyond this Curie temperature. and this is given for different substances. For cobalt it is 1394. In this diagram you can see for cobalt it is 1394. Means if you increase the temperature beyond 1394 degrees C, then this cobalt will be converted from ferromagnetic material to paramagnetic material. Its magnetization reduces. So this is how the ferromagnetic material depends on temperature and its thermal state. Iron can be converted into paramagnetic material at a still lower temperature, at only 1043 degrees C. It can be converted into paramagnetic material from ferromagnetic material. So the substances, ferromagnetic substances, have magnetism that depends on thermal state. It also depends on mechanical state. If it is moving very vigorously to and fro, then its magnetization is lost. So these are the things. Now one more thing I would like to discuss, the area under this curve, magnetic field and H. So area will be given by the product of the two quantity. Area of the curve is given by product B into H. So what will be the unit of the area under curve? So let me find, putting the unit of B and H. We know that unit of H is ampere per meter, and for B we can use Lorentz force. Force is equal to ILB. So from here one can find that unit of B is equal to Newton per ampere, and for length it is meter. So let me put the value of the unit of B over here. This is your Newton per ampere meter. Ampere is cut, so we get Newton per meter square. Now multiply the numerator and denominator by meter and you get Newton meter, which is unit of work or unit of energy. So the quantity will be energy. And MQ is the unit of volume. So this is your volume. So area under curve is giving energy per unit volume. Here you have the area given as energy per unit volume. Area inside the curve is representing energy of a unit volume. So it suggests that the energy we give as current electricity is not totally changed into energy gained as magnetization. Energy given as current electricity is not totally changed into energy of magnetization. Some energy per unit volume is lost, which is given by area under the hysteresis law. the energy lost per unit volume is given by the area under B versus H curve. So here you have the curve. Now if you draw the curve for two ferromagnetic materials like for steel and for soft iron, you will find that for soft iron the area is small. So if you take soft iron material inside solenoid, then whole of the energy will be converted as energy of magnetization and small energy is lost in that case. Here you can differentiate between steel and soft iron also. Steel has very high coercivity. So steel opposes any change in its magnetization if it is exposed to any stray magnetic field or it is exposed to any temperature variation or due to any mechanical upheaval, there will be a less chance of loss of or erosion of magnetization of steel. If you compare the area enclosed under the hysteresis loops of soft iron and steel, you will find that area for soft iron is smaller. And the area gives you energy lost per unit volume. So, smaller energy is lost in case of soft iron. The hysteresis loop of soft iron is made by red color. Here I am repeating it. So this is enclosing smaller area. At the places in the devices where the magnetic material undergo several cycles of magnetization, so if the area will be less for those materials, less energy will be lost. So in your transformer, in the core of transformer, in the diaphragm of telephone, we use soft material, soft iron only as core, as less energy is lost. And at the places where need to lose energy, like induction cooker or induction heater, so there we use steel. Magnet can be made by so many ways. One way is to keep any steel or iron material in north-south direction and hit it hard with a hammer. It can be converted into a magnet. Another way is way of stroking. So if you take a steel material or iron material and stroke it with a magnet in one direction with the help of a magnet by taking any one of the pole of the magnet and just pressing it whole along its length and again keeping it above away and again doing the same, stroking it again and again, pressing it from one end to another end by any one pole of the magnet. So by stroking in this way, you can magnetize any iron material. There is a two-way stroking method also. For that you need to take two magnets with their opposite poles at the center. One is if north pole and another is if south pole. Then stroke outwardly. Press with the two ends of the pole from North Pole and South Pole till its two free ends, and then again it put at the center and repeat this process of stroking again and again, and you will have this iron rod magnetized. So these are the methods. One method is to keep the iron material inside solenoid and pass electric current through the solenoid, and iron material will be magnetized. So these are the three ways. And we have some permanent magnets. Like your cobalt steel. Cobalt steel is one example. Another is your alnico. Another is your ticonel. So all these are permanent magnets. Also your lodestone, naturally found magnets are also permanent magnets. They are called lodestone or leading stone. So all these are permanent magnets. Now temporary magnet or soft iron. These are temporary magnets, and they have your hysteresis curve, you can see represented in red color. They have very small coercivity and they have small retentivity too. So if external magnetic field is removed, then it does not retain its magnetization. Its retentivity is also small. What is temporary magnet? The ferromagnetic materials which lose their magnetization as soon as external magnetic field is removed. Because they do not retain their magnetism, they have small retentivity. And because they do not sustain any external stray magnetic field, they do not sustain any thermal exposure or any mechanical upheaval, so they lose their magnetization, and so we can say that they have small coercivity too. But they have high relative permeability, as they are ferromagnetic materials, so their relative permeability is high. And they have high susceptibility too. So when these materials are used inside a solenoid, it increases the magnetization of solenoid manifold up to 1000 times. And these materials are used in your diaphragm of phone. It is used in the core of transformer. Some of the examples of permanent magnets are alnico, cobalt nickel, ticonel, and lodestone, which is a natural magnet. Now some of the examples of your temporary magnet, they are iron, cobalt, nickel, and gadolinium.